see on the right here is a kind of a cartoon of what's actually happening here. We replace the actin on the surface by LPA, and we can make the measurement using square wave voltammetry. I won't go into the physical chemistry of this, but for this particular audience interested in cancer wouldn't be so interested in this, but we can actually make the measurements electrochemically of all these various steps in the surface chemistry here. And basically we get a rather nice calibration curve. And I would sort of mention, this is actually in whole serum. This is not in a buffer solution. This is actually in a biological fluid. And basically, in this case, the limit of detection involving square wave voltammetry is around 2.5 micromolar, which is actually a bit better than the fluorescence method that we saw earlier. It's getting to the point where we can actually make this measurement in a real biological fluid. And we're actually embarking on some patient samples, which I'll talk about later on, what we're actually planning to do. But even this technology maybe not quite good enough. So we moved on to screen printed electrode types of device. This is a typical screen printed electrode. It's a micro device. The useful thing about this is it's very inexpensive. And basically, one of the things which I'll mention at the end of my presentation is you can put several electrodes on this type of device and actually interrogate them, and you can look at several biomarkers at the same time, which no one has done to this point. And I'll mention a few words about this later at the end of the presentation. But we've also used this particular device for the differential pulse voltammetry, which is, again, a different electrochemical technique. And basically, again, we have the surface chemistry of attachment just into the surface, and we can actually make measurements using this particular type of physical chemistry. We take several steps, of course: surface characterization, how to functionalize it, how to use it for LPA detection, and basically, we can set up a calibration curve, as you see here. The nice thing about this is that this particular method of differential pulse polarization voltammetry gets down to concentrations in serum, which are actually really quite low, sub micromolar. So that's actually become quite successful on screen printed electrodes. And as I mentioned earlier, it actually allows you to make multiplexed sensing systems, which I'll mention in a few minutes. Now, one of the things that we also trying to look at now is a completely different type of device. We're using electrical chemical impedance spectroscopy. The reason that we're actually doing that is that it's a much better way on screen printed electrodes to actually look at several types of biomarker. And one of the things that we're actually doing right now, we've not published this, but we have two postdocs doing this, is we're trying to look at 3 different biomarkers on one interrogatable device. And you need electrochemical impedance spectroscopy to actually do that. And we can do that using screen printed electrodes. This work we're doing, incidentally, is collaboration with the Tyndall National Research Institute in the Republic of Ireland. These folks in Ireland are the world experts in device technology for biological systems. It's a very large European institute, and they're experts at electrodes and microelectrode technology. So we collaborate extensively with that group. We had 2 students over there recently, and they send people to us in Canada. So this sort of device in this field, where you can look at not just one biomarker, but several on one device, is a sort of very new area, in the sense that so far, to this point, nobody has actually done this in a very practical way. So hopefully within a few months or a year or 2, we should be able to have this available, using the kind of surface chemistry that you saw a few slides, at least summarized a few slides ago. We also have embarked on a somewhat different approach recently. Many of the audience here will be familiar with ELISA-like technology, lens-linked immunoassays, which is a major, of course, a major technology used in the standard hospital clinical biochemistry lab. And a couple of years ago, I gave a presentation to one of the local hospitals here in Toronto about our research on ovarian cancer detection, and they said, they pointed out to me that they would like to see a sort of technology that actually reflects or looks like ELISA-like technology, simply because they could then incorporate this sort of strategy into their standard approach. And so we embarked on this about 2 years ago, or a year or two ago, rather different approach to this, but using the same molecular chemistry, but now using a completely different approach. And in this case, we're using ion-based nanoparticles. As I'm sure the members of the audience know, in standard ELISA-like technology, they use magnetic particles with an immunoassay attached to that, and then they separate the particles out by magnetic field. I'm sure that everybody in the audience is pretty familiar with that. But we have a very similar system here, excepting the chemistry is the chemistry that I've looked at in my presentation already so far. So basically, we can actually, in this case, make a chemiluminescent measurement of actin, which is replaced by LPA on the surface of these ion nanoparticles. This required some pretty heavy-duty research in nanoparticle chemistry, actually on the surface. And this has been occupying a PhD now for a year or two on this effort. So basically, we have to take several steps here. Much as they do in ELISA, by the way, using iron oxide nanoparticle, we modify the surface in several steps to get the kind of surface chemistry that you've already looked at using nickel and the standard nickel NTA system to do this, which is very common in ELISA type technology. And so we modified that and used it for the gel cylinder probe type acting system that we've seen already in my presentation. So we actually have been looking at this for about a year or a year and a half now as a method for doing LPA. And we use the similar surface chemistry. We could put on our antifouling chemistry on the surface of these nanoparticles, much as we saw earlier on. And we have a nickel histide type approach to get the gel cylinder probe on there. And basically, as you can see here, and basically, we can then make a measurement of the chemiluminescence. In this case, we use actinium dye on the actin. I won't go into the physical chemistry of this, but we've done an awful lot of studies of different concentrations of dye in solution. And basically, the end result of this is basically we can make a measurement of LPA using chemiluminescence, using very, very similar like ELISA approach. And this actually becomes sub-micromolar in the nanomolar area, which is really excellent for looking at stage 1 concentrations of LPA, as we saw earlier. So this is actually really very promising because the oncologists and the clinical biochemists very much like this approach because, as I mentioned earlier, it sort of fits in very well with their standard roboticized ELISA-based system that we use for many other types of clinical biochemical measurements. So we actually right now are actually having this tested out at the clinical biochem lab at St. Michael's Hospital here in Toronto, and also Princess Margaret Hospital, the two big teaching hospitals here in our city. They're actually now working towards trying this out on patients, which I'll mention again in a few moments. We also have been started a relatively new project using acoustic wave detection. This is devices which actually operate by vibrational frequency. Some of you in the audience may be familiar with these devices. Basically, they're based on piezoelectric physics. Basically, we can attach the very, very similar chemistry that we saw earlier onto these gold surfaces of these types of device. They actually operate by vibrational frequency, which is anywhere ranging between 10 megahertz and about 1 gigahertz, depending on the device. I don't have time to go into the physics of these things, but we have two types of device. One top right there is called a thickness shear mode device, which is some people call a quartz crystal microbalance. On the bottom left, we have a very high frequency system which operates at 1 gigahertz, which operates via a flat spiral coil, which drives the crystal, quartz crystal into a vibration. So we can actually put the chemistry that we've seen on several devices so far. We can put these on these types of devices. This is a very new project in our lab. We've not made any publication of this yet, but we're about to do just that actually. And so basically the chemistry, as you've seen, is already very, very familiar to the audience. Nickel Istai using a gelskin probe system, which now is going on gold electrodes or silica electrodes. And basically we've been able to detect lysophosphoric acid using serum, using the antiphthalmic chemistry that we saw earlier on. And this is very, very early work. This is very recent work in our lab in the last few weeks. And basically we can actually develop a concentration curve based upon signals we get from LPA in whole human serum. Again, this is not a buffer solution, this is human serum. We're trying now to measure the limit of detection of this in serum and see how this compares with the other methods that we looked at earlier. So I just wanted to mention that we get quite a bit of funding from these different institutes. I want to spend a couple of minutes talking about where we go with all of this. We're trying to find out in our lab which would be the best approach to the sort of clinical biochemistry lab to do very large scale screening. Clearly, if you're going to try to develop a system where you're not just screening, you're screening potentially millions of patients annually. Clearly, since at stage 1, well over 90% of 5-year survival at stage 1 of this particular disease, which is very well known in the world of cancer technology. So if we could screen, very large numbers of patients, women over, I don't know, whatever age you want to choose here, really could make a major inroads into prevention of the disease. But we don't really know at this point what would be the most practical way of doing this, which is the clinical biochemists want to test it's highly sensitive. They don't want any false positive negatives. They want it to be very inexpensive for obvious reasons. So this is quite a challenge. We've got to sort of evaluate the best approach to this. Do we need to have, for example, the square wave voltammetry or differential voltammetry, or is electrochemistry the way to go? We're trying right now to do a very detailed comparison with that standard CA125 assay, which, as I mentioned, has been around for a very long time. How does it compare? One of the things we're doing right now is we're taking male blood, which has no LPA in it, and we're actually spiking it with LPA and testing out our system. So what we do is we get one of our male graduate students to go to the hospital. They take blood, they spike it with LPA, and then the hospital is actually doing the actual assay to find out how good this is. At our local hospital here, the Princess Margaret Hospital in the city of Toronto, they have patient samples from stage 1 through 4 available to us, and we have the approval from the authorities to actually look at these things. So we're actually testing these out as we speak. And finally, one of the rather exciting things that we're trying to do here, as I mentioned already a few slides ago, is we're trying to actually develop a multiplexed biomarker system which looks at several biomarkers at the same time on the same device. this is a heck of a challenge to the biosensor specialist. Actually, it's not simple at all to do this. But we are collaborating with the right people here. That is the guys in Ireland, which are experts at this. So we're actually hoping within the way things are going, within a few weeks or a few months, we should be able to have a sort of prototype device for that using screen printed electrodes and electrochemical beam spectroscopy on the surface. And that would be, I think, sort of quite an exciting possibility, not just for screening patients, but also to do comparisons of how these different biomarkers behave with this particular disease. Because as everyone knows in the world of cancer, ovarian cancer, there are a whole bunch of different cell lines involved here, so which involve different biomarkers. So clearly this will be an advantage. And down in the future, possibly down, in some years, we may be able to look at, half a dozen or even more biomarkers on one device, which would be a major step forward in detecting this particular disease. Okay, everybody. So I hope that was useful for everyone. And this is actually my email address if people want to contact me. This is our city of Toronto. That is the CN Tower there. You see there, 1,800 sort of feet tall. It used to be the tallest freestanding structure in the world until that thing building got put up in Dubai over there, the United Arab Emirates, which beats it by about 20 feet apparently. So it's the second largest, tallest standing structure in the world now. So I'll finish there, and I'll be happy to answer any questions from the audience.
Thank you, Dr. Miguel, for